Hello, welcome back. So in the series till now we have been trying to do bilanguage, bigram language modeling, wherein we take one token. In our particular case, it has been one character. We input one character and we try to predict next character. So that is how we have been trying to do the things. We follow two ways of calculating counts of each bigram uh, and modeling a neural network for taking one character as an input and another and predicting another character as an output. So this has been okay so far, but we could do much better by getting making our models complex a bit and also trying to learn the word represent or character representations a bit better. So if you remember, we converted a token that's going input as an input to neural network into a one hot vector, which is nothing but a sparse vector, all zeros, and doesn't as of as it doesn't have much information about the character or the words or tokens. But what we can do is there's approach to learn representations of each of those characters in your vocabulary in a smaller dimensional space, uh, which has been introduced in a paper, and many other approaches of using a multi-layer perceptron for modeling next token prediction or next character prediction kind of problem statement. So this paper, I want to highlight a few important things out of this paper, and then we'll try to implement it using code in Torch. So basically, this paper says that it tries to learn a distributed representation for each word. So distributed representation is nothing but reducing the dimensionality in which the token or a character in out of all the vocabulary is represented. If you use one hot vector representation, um, it is a sparse way of representing the vocabulary in a high-dimensional space. This approach, wherein we transform it into a smaller dimensional space and try to learn dense vectors out of it, that would be one takeaway from this exercise. Then another is it will try to learn the probability for word sequences or the character sequences that we have done in the last approach as well of neural network. Now, another thing that is important here is so this is the same thing that if in this paper, the problem statement, they took their vocab size of 17,000, which was a word level vocabulary. We have a character level vocabulary, which is pretty small. So for 13,000 vocabulary size, the one hot vector would have been of length 17,000. They compressed it into a space of dimensional space of 30 or 60 or 100. So that's a really good compression if they were able to represent the words, learn the representation of the words into such a small dimensional space. So we'll also have to do something similar where in our 27 dimensional one hot vector sizes will have to be represented in some smaller space, maybe 248 something, we'll see. Then the objective of learning this model would be maximizing the log likelihood, which is same as minimizing the negative log likelihood. And plus also we'll be putting a regularization term to it, with decay. So from this exercise, what happens is, if you know that dog and cat played similar roles, for example, semantically and syntactically, similarly, the A and the are playing similar roles. Bedroom, room are playing similar roles. Is and was are playing similar roles. Running, walking are playing similar roles. So in our training set or test set, if the training set has, we could normally generalize from the cat is walking in the bedroom to a dog is running in a room, because here the and a are kind of playing similar roles. Cat and dog are syntactically and semantically similar. Is, was are similar. Walking and running are kind of similar. So if even if we have not seen these sentences in our training data, only this, it it should be able to assign a relatively higher probability for this sentence to happen it because the words like the a would fall um, close to each other in a lower dimensional space that will in the representation of the words or tokens. So it says that because the probability function is a smooth function, a small change in probability, the presence of only one of the above sentences in the training data will increase the probability not only of that sentence, but also of its combinatorial number of neighbors in sentence space as represented by sequence of feature vectors. So it's the same thing. If even if we have not seen all these sentences in our training data, we should be able to assign high relatively high probability if we have seen this sentence, because there are a lot of words in similar that fall under similar dimensional space in same area in the dimensional space where we are representing. Then another thing, if we look at the diagram of this paper, it uses a larger context window that goes in input as to the middle layer of the neural network. So in our previous neural network example, we are taking one character input and we are out predicting another character. So here now we are not just taking one character or one token as input to the neural network. We're taking three uh, last three characters or words or tokens into a neural network. So it is index for wt minus n plus 1, t minus 2, t minus 1. So we three last three characters getting going into input to this neural network. Before going into the hidden layer, they are being transformed by a lookup table. So lookup table is nothing but a kind of embedding matrix, which is also be a form of weight matrix of the different dimensionality than this. But will this is the lookup table or embedding matrix that will transform the index of the words or characters in our case into lower dimensional space. So right now here at this stage our dimensional space would be of 27 length. Here, after this, it would reduce drastically to, let's say, 2 or 4. And then once we have each of these context words or characters in lower dimensional space, all these three representation of the words go into the hidden layer. Here we can have 100 or 200, whatever number of neurons, which would be transformed with 10H nonlinearity and giving as softmax of our vocabulary size. So this layer would have size of neurons equal to size of our vocabulary. In the case 27, in the case of the paper, it is 17,000. So this would be a pretty large layer there. And we apply softmax of exponentiating and then normalizing it to get the probability distribution out of it. So most of the part of this network looks similar, only difference is that we are now using three uh, words or characters going in as inputs, and before hidden layer we are using a lookup table or embedding matrix to transform them into a dense space. Now let's get into the coding part. Okay, so let's start with the fresh notebook now. Uh, we read in the names.txt file. The total number of names in our data is 32,033. We look at first five words or names: Viva, Emma, Olivia, Eva, Isabella, Sophia. So in our previous examples, we were building for neural network data in a form that where one token is input and another token or character is output. Now here we'll have to build our inputs quite differently. So in our so before building the data, let's build a vocab. It would be similar to what we did last exercise. Stop set of words. So it's in this order that we want. Therefore, vocab size equals to length of vocab. Now we build the mapping S2I for CH in rate vocab. There is nothing but CH for I and I to S for character into I dot tense. So 0 corresponds to dot and 26 is for Z. Okay, so we have built our mappings and vocabulary. Now we can go on to build data. Um, so we start with empty lists. For 5 names, let's do it. Uh, Context is so this PC is directly from the paper. Block size is 3, wherein we are taking 3 tokens of actors going it as input in the neural network. So that's why we'll define context as of block size 3. So once we have context of then 3, it is a list of 3 zeros which will represent in W. So context is this. So we are iterating at each characters in the word plus W dot, because dot will be the token where our generation ends for these. So for this, ix would be equal to s2I. We transform this character. We do x dot append context and dot append ix. So this is first example. Once this is done, we'll change context is equal to context, the last 2 characters in context plus ix. Before changing the context, let's print out. So we want to print the context for I in context. Join address I. So for each integer in the context, we get the string corresponding to that integer, and then we join all of those, so it will make a small string. And for this string, we say our output is I2S of IX. Yes, so this is what we want to print now. Context will change because we have taken this example where this is the context and the is the first token from this word is the outer is the y. Once you have done this, we continue. Now context has changed. Our next character in this string will identify the index corresponding to it, and then we append the new context, new output. So let's see what does this do. Maybe let's do it for 3 words. All right. So you see for word Emma, first sample is 3 dots input, E output. Then 1 dot gets out, 2 dot and E is input, M is output. In the end, MMA is input and the dot is output, at which point this word stops. Similarly for Olivia. So Emma has transformed into 5 training samples. Olivia has transformed into 7 training examples, so on and so forth. I'm just going to print it. As we transform this, torch.tensor will again do same. Y equals to torch.tensor of y. X, Y dot shape. Okay, so out of these 5 words, 5 names in the training data, we have made a training set of size X is of size 32 by 3, where 3 belongs to the block size context and 32 samples. And Y's are 32 integers basically. These are all integers. Okay. So now next thing is to we have a context window X going in as input. So let's say this is our X. So at a time, at at an instance, network will be taking this one vector as input, which will be a context window of 3 tokens or 3 characters going in. So these 3 are integers, and we need to convert these into one hot vectors, which would then be transformed using an embedding matrix uh, of a smaller dimensional size. All right. We saw that we have x and y's of shape 32 by 3 and 32. So now we'll have to, as per the paper that we looked at, we need to have a lookup table, and from that lookup table, we'll have to map each of these integers into a lower dimensional space. So ideally what we want is each of these integers, which represent a character right now, to have a representation of some dimensionality, let's say of 4 dimensions representation or something. So earlier in previous neural network example, we saw that we converted each of these into just a one hot encoding vector. So that was a 27 length vector. But here we don't want to waste so much space, and we don't want them to be having a lot of zeros. So instead of converting them into one hot vector and giving into the neural network, we want to convert them into a dense vector representation. So basically we'll need to have a lookup table. So let's say lookup table is C, which is, okay, I think let me restart this. Yeah, so let's initialize the embedding matrix or the lookup table. It should be with the shape 27 by 2 because in X, each of these integers can be the one hot vector would be of size 27, and we want to transform them into size 2. So output dimension that this embedding matrix should give is 2. So this should be our lookup table. And if we want to now let's say if ideally what we want to do is if X is our example, this one, let's reduce the size of X. Let's make it 2. Just 12 data points. So for these are 12 samples going 12 sample inputs. Each sample has 3 tokens or characters, integers corresponding to the characters. Now each integer will get transformed to one hot vector of size 27, and then from using the C embedding matrix we should get two-dimensional representation for each of these input. So ideally if x dot shape is if x dot shape is 12 by 3, we should get after looking up from this table, we should get the shape of 12 by 3 by 2. So for each character represented by the integer in this 3, we'll have two-dimensional representations. So how do we get this is you just index into C with X. So what this does is now if you see dot shape, this shape should be 12 by 3 by 2. Yes, it is 12 by 3 by 2. So what it does, this statement is C of X indexing with X is at each integer value of X, it returns the um, um, that row of the C. So suppose if you talk about X of 0, right? 0 and 0. X of 0 is this. So this is corresponding to, they will get 3 two-dimensional embeddings coming out of it. Now if you compare C of 0 should be the same thing. It is the same thing that comes here, right? That means what it does is 3 times 0th row of the C has been plugged out and put into the place of the 0, and the 0. So this 0 becomes a two-dimensional element, uh, another 0 becomes another two-dimensional vector, and so on. So that's how we embed or look up for each integers in the X, and this will transform our, this will become our embedding. Now, once we have our embedding, we can build our um, hidden layers basically. So let's say we want to build two hidden layers. So two hidden layers will have weights and biases, and second will also have the weights and biases. The shape of this should be now. The shape that it should take input is 6 and output is let's say 100. Where does say 6 comes from? 6 comes from, if you see m dot shape, right? So this has 12 samples, 12 examples of 3 by 2 dimensionalities. So there are two-dimensional vectors and three vectors such. So they will combine, we'll have to concatenate them, which will become six dimensional vector, and it will go as input into the first weight matrix. Once this is done, let's make it 4000 and then 100. So second will take 100 as input, and it should give, maybe let's say 27 as output. 27. So now that we have initialized our weights and biases, let's calculate hidden state uh, output, which would be embedding matrix multiplied with W2 plus B2. So this will be embedding weight is embedding size shape is, so we are not multiplying it as is. We'll reshape it as 6. So this would become 12 by 6 shape, and you matrix multiplied with weights, which is 6 by 100. So in the end, return we'll get 12 by 100 shape matrix, and we have 100 dimensional B1, so it will directly just add it to each of those elements in each sample. Once we have H dot shape, okay, wait. So multiply it with by 6, right? Oh, sorry, my bad. W1. Yeah, and also one more thing is we need to apply some activations on it. So we can do torch.10h. Now the shape of h is 12 by 100 as we understood. So, sorry, this happens on top of all of this. So once you have calculated linear combination of yx plus b, x w wx plus b, then we perform a activation of 10h on top of it. And once we have this, we'll calculate logits now, which should be h matrix multiplied with w2 plus b2. So this shape should be 12 by 100 matrix multiplied by 100 by 27. So this should be 12 by 27, right? Dot shape 12 by 27. Now that we have logits, we can do a same calculation of exponentiating it and then um, finding out the normalizing it throughout the rows as we did in our last example. So let's put all of these things in a one cell. Now we calculate counts, which is nothing but logits dot exponentiated. We calculate probabilities, which is nothing but which is counts divided by counts dot sum keep them equals to true. So this is probability we get. Probability of shape would be 12 by 27. It should be the same. Yeah. So we now have probabilities. Now we can calculate loss out of it. Losses minus of probability. We index into these torch dot arrange x dot shape 0 wise. By doing this, we get the correct the probabilities at the correct indices at the target indices for each example. We take log of it and we do mean and we do negative of it. So this would be the loss. Hmm, isn't that correct? Should be correct, I think. Maybe for now, let's say that. Okay. Yeah. Okay. Now you see the loss coming out is 15. So once we have the loss, we can okay. Now we have the loss. We can do the back propagation to it. But before doing the back propagation, we need to do one thing. Um we need to do requires grad true in for each of these W's and B's, right? Is equals to W1, W2, P2, C. So this can also be a way of doing require grad equals to 2 in all of the parameters. You make a list of all of the parameters. This way it would be easy to count the list of parameters. So there are 3,481 parameters. We have triggered requires grad for equals to 2 for everything. So now for we need to do for p and parameters p dot grad equals to none. We do zero out the gradients in each of the parameters and then we call loss dot backward. Once we have loss dot backward, we'll have to perform updates. What's wrong happening here? Unsupported operand type. but mm, type of p dot grad, type of p dot data. Let's print these. So first time loss gets printed. When it comes to this, tensor and tensor. Okay, so I was making a mistake. I'm not sure why the C was not included here, while the initialization and the calculation of embedding uh, lookup of from X is not was not included in this cell. Maybe that's why loss was not being, but it should have been calculated. But yeah, anyways, now we are able to run one iteration of parameter updates this way. So first iteration 17.2054. If we keep running this cell, we'll see that loss is coming down, keeps coming down drastically. Not bad. So now we are at a point where we have made a complex network, learned some embedding lookup table, uh, which can transform 27-dimensional axis one hot vector into two-dimensional embeddings. Then we made two layers of neural network, hidden layers, and we calculated the loss from probability distributions, and we did the back propagation. We did the parameter updates. So now let's say we have reduced it to a certain point. We can try to sample from this. So we were able to reduce it so fast to 1.14 because we were uh, considering very small data set. You see only 12 samples. Now let's expand it to entire data. Then let's initialize the weight. And so now we won't be able to do this as easily. So and then we print the loss. We do it for 1,000 iteration. Let's see what happens then. All right, now let's let it run. So I let it run for a while. It was taking pretty long, and also the after first print, here onwards, the reduction in the loss wasn't quite as much as we would expect it to be. And also for each iteration, it was taking pretty long now. So one problem is that right now, our embedding or our X contains entire data set. So for doing all these calculations for entire data set are pretty heavy. Uh, Whereas, after doing calculation over entire dataset, it performs back propagation and only one update. So that is not very effective because although the gradients are correct, but it's taking pretty long. But if we break this data into mini batches, small batches of a set number, um, it should be able to perform these updates quite frequently in the similar direction. Not as accurate, but it should be in the similar direction, and eventually it should reach there. So we'll try to break it up, but before that, I removed all the magic numbers and converted them into variables. So embedding dimension I have defined as 2, number of hidden is 100, and block size we already defined up somewhere is 3. So we have all these parameters in terms of the defined variables now. Now let's break this. Let's find a index array in the range 0 till out shape 0, and size would be, let's say, whatever we can define another variable for batch size. Let's say we keep it as 32 for now, right? So here we can say it should be batch size. So with this toss.rednet, we'll get a list of or a tensor of integers, batch size integer, which is 32 integers between 0 and x dot shape 0. So if samples in x is, let's say, 100,000, between 0 and 100,000, we'll get these many integers, random integers. And from those, we can say that xb, yb is, these are the mini batch embeddings we get as C index with xp, w1, w2, h. Here, while calculating loss, we need to use yb and xb. Then otherwise it's alright. I think let's see now what happens. Cool. So it reaches to somewhat similar number, not as bad as good as last time, but it take way less time. So maybe what we can do is we can try to increase the learning rate. See where it goes. Okay, that's not good. 0.1. Or let's try with 1. What happens? It's not increasing as much. Let's increase the number of we are doing for 1000, or do it for 10,000. 2.3. Let's say we do it, we print here for thousands. Learning rate 2.2. Okay, so here you see it went at 2.07, but again it got increased to 2.4, 2.5. Means at this point, around, let's say after 20, 30,000 iteration, it starts to saturate. 1000, 0.01. So now let's run optimization again. And so see, eventually we have reached to a point where we are already below the loss that was being achieved with her previous neural network and the count-based methods, which was of the order of 2.4 something. So we have already surpassed it. Yeah, now let's maybe let us try to sample from this, see what comes out. Sorry. Bashono, Chloe, Eden, Chikri, Emma, Tari. Okay, something sensible. Not much better than our previous models, but something's happening.
So one thing I've changed in my network or the optimization steps is I've replaced all these three steps with just cross entropy, f dot cross entropy. So we just pass the logits and targets. It will give us the loss. So after training it, I've been able to reach in 30,000 iterations to 2.2 loss. Then also I try to calculate because these losses that are getting printed are over a mini patch. I printed it, I calculated loss on the entire training set. It is 2.373475. Generating names looks like this: Chuka, that, male, Maima, so on. So now one thing is we have been randomly experimenting with the learning rates, zero point 0.1 for this much range, then 0.01, etc., etc. Now what I want to do is we want to understand how is there any approach to learning uh, how to start, how to find the correct learning rate to start with. So one thing you can think of is ideally we look generally we want something between let's say 1 or between 0.0001 to 1, something in this range. So we can say that it is something in the range of 10 to the power minus 4, 1, 2, 3, 4, to 10 to the power 0. So in this range, if we, let's say for this example, let's reduce our search space. So there's a function in PyTorch, torch.lenSpace. What it does is between two ranges, suppose if we want to generate from -3 to 3, in two ranges -3 to 0, we want to generate 100 numbers or 10 numbers. So it generates 10 numbers at equal intervals between -3 and 0. Right? Similarly, instead what we can do is we can generate 1000 numbers in this range. So this would be a lot. We can say that these are LR, learning rate exponents. So learning rates would be nothing but 10 to the power of LRE, and this would give us 1000 learning rates which range between 0.001 to 1, because these are the exponents. We are taking 10 to the power of exponents of each element wise exponentiation. So you get, so if you see the learning rates, it starts from 0.0010, which is this, and it keeps on increasing possibly, and it reaches 1 at a point. So now what we can do is, if this is our learning rates we want to experiment on, let's bring back our optimization steps. Initialize all the parameters and we run the optimization now. So optimization will only run for 1000 steps, where we will be doing one step for each learning rate. Loss I, we will have to store losses learning rates to in the end plot and see which learning rate is suitable for us. Here we don't need to print this line of code. All right. LRs of I. So at every instance, we'll change the learning rate. We'll pick a learning rate from this by indexing I. And once we have done this, LRI dot append LR loss I dot append loss, right? Now let's run this, and we are not printing anything for now. Okay, now what we have to do is purity dot plot. It would be just on the x-axis we want our learning rates, on the y-axis we want our losses. See what happens. Sorry. Instead, sorry, we'll have to reinitialize this and the equation. Cool. So you see how on the x-axis it's learning rates ranging from 0.001 to 1. Maybe let's plot learning rate exponents instead. Yeah, so that makes more sense. Here are the exponents ranging from -3 to 0. The loss is reducing. So at this point, -1 learning rate exponent, the learning rates are lowest. So yeah, this is the plot that we get for the losses. So we see around -1 exponent, we get the lowest loss. Therefore, we just our intuition of using loss learning rate of 0.1 and then after some iterations 0.01 should be okay. So I've let run the optimization steps again for 100,000 steps with 40,000 steps of learning rate 0.01 and then 0.1 and then 0.01. And if you see, the lowest loss I was able to achieve on in that range set is 2.3008, which is uh, better than our previous experiments with neural networks or the count-based methods. So I tried generating with the same updated weights, and it is doing a bit better job again. Anna Juma Eniam, Try, Elion. They sound name like, not sure if they are actually names or not, they might not be. But yeah, this is what we have been able to achieve. After this video, I'll try to see if I can do even better with some. Uh, okay, so one experiment we can obviously do is we can increase the embedding dimension size. All right, let's see what happens now. When increase the embedding dimension size, this should be block size times embedding dimensions. Okay, so we got a further reduced loss 2.23 when we increase our embedding dimensions from 2 to 5. So let's see what the names get generated now. Sorry, it should be changed. Block size times embedding dimensions. Island, Oimon, Su, Cell, Elias. Maybe they're name like, yeah, doesn't sound that bad.